Morning. Second day. I'm 0xv23.0, also known as Timo. I have a workshop about tracing Bitcoin Core. And I have a few questions at first. Who here has a Bitcoin Core node running? Show of hands. OK, more than half. Who here compiled Bitcoin Core from source at least once? OK. Who here sent me an ssh pubkey beforehand? OK, cool. The others, like, this is only needed for the workshop part, but this is going to be the majority of the time. So if you want to participate there, you have to do that like now, or otherwise I probably don't have the time for setting something up for you. There are instructions on the prerequisites, email and everything that probably went to your spam or folder. So, like, not from me, from the conference, but yeah. And yeah, that's pretty much it for setup. I'm going to start. And one thing I'm going to ask you is please don't take photos. We have a recording here, but they're going to blur out my face or something. I don't like having my face on Twitter or something. And I'm sure we can respect that. Yeah, OK, let's get started. So tracing Bitcoin Core version 23.0. So in the latest Bitcoin Core release earlier this year, we had something called trace points in it. And trace points are something that help us to hook into a running process and extract some process internals from it. And one example is here. That's not right. One example is here, a tracing script I built to showcase some of the functionality. So what we have here is a Python script that hooks into a running Bitcoin Core instance. And each time a message is sent or received from a peer, we get the event notification of it. And we actually can build applications that use this information and so on. Yes?
I just have a brief question about tracing. If you could just explain why you need tracing and you can't do the same with like print statements.
Yeah, that's the next slide. So yeah, no, awesome. Yeah, cool question. But yeah, just a quick demo at first. So we can actually see, for example, in my node, exchanging transactions with another node and sending messages back and forth. And there's multiple like node connections we have, and they all do something different. And I think that's great for example, educational purposes, but also for debugging or development. And that's a tool, I use, for example, to review Bitcoin Core PRs. Yeah, that's the same as shown here in the video, just in the live demo. Yeah, as mentioned, I'm Timo, 0xv23. I'm supported by a Brink dev grant. Thanks, Mike. I've been working on some observability projects for the past few years. So I run a mempool observer. I run a mining pool observer where I see if any pools are censoring transactions, for example. I've been working on Bitcoin Core here and there. For example, the trace points were a big project of mine in Bitcoin Core. I have a transaction feed.info site and so on. Yeah, been around for a few years. Yeah, and most part of this workshop is like being the second part, the hands-on tracing part, where I give you access to a VPS, and you do the tracing tasks I have prepared for you there. And so you don't really have any setup on your machine. This is all running in the cloud, but you need to give me an SSH pubkey for that. Otherwise, I can't give you access to a machine. And now we're going to start with like 15 minutes or so of background. And getting to your question, why do we need tracing for Bitcoin Core? The buzzword here is observability. And the goal is to gather like the low-level process internals. So what's happening in the software? And the goal for Bitcoin is to become like an open currency for everybody to use. And Bitcoin Core is at the moment the backend that most people use, as we saw, like most of you actually run a node, and it's probably Bitcoin Core. But I'd say Bitcoin Core is a black box to many. And even like there are only a few people in the world that actually do know what it's doing, really like over like all parts of it, and it's doing a lot of complex things, and we want to have a bit more insights into that, and actually want to know what the code that we wrote at some point is doing in production or when we run it, for example, to power a Lightning node and so on. Yeah, in general, like the tracing helps with robustness and security. And now to your question, what other interfaces are there exposing process internal state? Does anyone know an interface?
A log file.
All right, a log file, yeah. And that's your question as well. Like we have the debug log file in there, and we could add print statements, but print statements or debug logs are more like a human interface, machine-to-human interface. And with tracing, we want to have a machine-to-machine interface where we can have applications that like use this information and so on. And like we could parse the log file, but this is like an indirection. We don't want to necessarily make this step. Any other like interfaces that Bitcoin Core has?
RPC.
Yeah, RPC and the REST interface as well. Yeah, that's pretty much the same. And there is one more I have in mind. Yeah. ZMQ, correct. Yeah, your blocks and transactions over ZMQ. Yeah, that pretty much are the interfaces we have. And now we have a tracing interface as well, if we want to use it. And for tracing, we choose Ebpf and USDT. This is not Tether. I'm going to get into it, and yeah. No. Oh, this wasn't finished. So yeah, tracing is one of the tools that is being like a part of like the toolkit that Bitcoin Core developers or users could use or can use. So yeah, some additional to making Bitcoin Core more robust and secure and so on. Yeah. Now we get to the Ebpf and USDT part. So what is Ebpf? Ebpf, so the Bpf thing stands for Berkeley Packet Filter. I'm not sure if some of you are familiar with Wireshark or TCP dump. The Berkeley Packet Filter is like the underlying tech that does this, and this like from the 90s or so, or the 80s. And really early on, to filter packets that are being sent to a host, to the kernel, and record them, for example, or analyze them. And Ebpf is an extension from that, so we don't only look at like network packages, we also look at everything else that is happening in the kernel. And we have, for example, trace points in the kernel, or we have trace points in a user space application like Bitcoin Core, for example, and we can run in an Ebpf virtual machine in the Linux kernel some program that's mostly user-defined. It's executed by the kernel. Previously, you would have done either kernel source modifications or something similar, and you risk like crashing the kernel or hanging the kernel or like crashing your machine, and we don't want to do that, so we use the Ebpf virtual machine and can attach like a small program in the kernel in a virtual machine that can't crash to a trace point. So each time the trace point is called, this small program is executed and does some funny things with it. And Ebpf is really powerful, and we can use it for security. One example here is what we have in Bitcoin Core right now. Still experimental, but we can use this to block certain syscalls that we know Bitcoin Core shouldn't make. So we can limit the functionality to say, okay, if an attacker somehow does something funny with Bitcoin Core, it shouldn't use this call. It should only use this whitelisted syscall, for example. Also, Ebpf can do networking, so we can like have DDoS mitigation, for example. So before even like a packet hits your HTTP server, we can reject it, for example. We can do profiling and benchmarking. This is also really interesting at the concept of Bitcoin Core. Yeah, 1 second. Here we also have been doing some parts of it, and observability is like the thing we're going to focus on today. Yes?
So that Ebpf that's occurring at the network part, not before it reaches like the
so with Ebpf, we can actually hook into, like here, we can actually hook into the network card and say, okay, before it even hits like our user space, like our web server, for example, we can reject the package. Yeah, and we're going to focus on the observability part here today. Yes, and we have two versions of trace points, or two kinds of trace points. We have either dynamic trace points or we have static trace points. We focus on the static trace points in the user space in Bitcoin Core here. But there are also people using DU probes, for example, dynamic trace points. So that means we can attach to a function, and each time this function is called, we get the input arguments to that function in like the Ebpf virtual machine. We don't do that here, but today we use static trace points. I'm going to show you some in the next slide. And there are, we have like documentation for these, and they are expected to be somewhat stable. So between releases and patches and changes, they don't change, and we can reuse them in scripts and so on. Functions often change, so that's why we don't use the dynamic trace points, at least here. Yeah, and USDT, again, not tether, user-spaced, statically defined tracing. We can decide to hook in some trace points. So for example, I showed you earlier the example where I hooked into the P2P message trace points, so sending a message to another peer. And we can choose to hook into like only incoming messages, for example, or only outgoing messages, depending on what we want to debug or trace or whatever. And you can think of it like there's the execution flow of your program, and once the trace point is reached, the internet state that is being passed as an argument to that trace point is passed to the Ebpf virtual machine. And you can think of it like, who here is familiar with like GDB or some kind of debugger in development? Yeah, some are. So once like you reach like a breakpoint in the debugger, you're going to halt the program and do something else. And in this case here, we pass the state to the Ebpf virtual machine and process the arguments there. Also, like USDT is not super exotic. It's also used by Postgres, MySQL, Python, Node.js, glibc, and a bunch of other libraries, for example. It's not always activated or compiled in. It's sometimes like an opt-in feature. For Bitcoin Core, we have decided to do it as in the release builds, it's enabled. So if somebody is running Bitcoin Core in production and is using the release build, they can definitely hook into the tracing stuff. And if there's a problem, detect it and trace it, debug it. So how does these trace points look in Bitcoin Core? We implemented them with system tab. That's not really important what that is right now, but it's like a compile time dependency. If you have system tab on your computer installed, then, or in the build machine installed, then it compiles these trace points in. And these trace points are basically like a ELF node. If that's too much for you, like if you don't know what that is, that's not a problem. We're going to see that in the workshop. But yeah, it basically like saying, okay, here's like a trace point in this address in the binary, and in the binary there is actually like a knob, like a no operation, and we set like a breakpoint on that knob, and each time that knob is reached, we execute the Ebpf script. And we use some fancy macros here where we can pass arguments from 0 to 12, and also we have like a context and an event. So this is an example for one of the trace points I used earlier to show you in the demo. This is the net outbound message trace point. So each time we send an outbound message to another peer, this trace point is called, or reached at least. And if you hook into it, something is passed to the kernel. And here the context is net, and the name is outbound message. We send a bit of information about the peer, the ID, the address name, which is actually like the IP address formatted, or the onion address or so. the connection type, if it's an inbound, outbound, block relay only, for example. The message type, like what message is this? Is this like a new block, or is it a transaction, or is it even like a IP address that is being gossiped? And we send the message and the message size and the message data. And then we need some tooling to hook into these trace points. And there is currently two things we use. One is Ebpf trace. You're going to use both in the workshop part here. Ebpf trace is more like a high-level language, really for basic and short scripts. And you're going to have a hard time if you do something else than printing logs or histograms or CSV files. Then on the other hand, we have the Ebpf compiler collection, BCC. That's more like a toolkit that we can use to build really like complex tracing programs. I've used that in Python and in Rust, and you can use it in C++ and Go and so on. And you can build like really tools and like things that pass, for example, data into message queues and so on here with that. Here's an Ebpf trace example. It's like 40 lines of script here. What we do is we have, can you see my mouse pointer? Yeah. We have here, we say, okay, this is like a USDT trace point. This is the binary we hook into. In source Bitcoin D, that's something I just compiled. Then the name of the context is net, and we hook into the inbound trace point. And then we fill out these variables with arguments that are being passed to the trace point. That's this here. And just print it out. That's Ebpf trace. And BCC is a bit more complex. We write a small C program, define a function that collects the data, and in line 10 prints, or not prints, but sends the struct we filled into a Ebpf map. It's not important what this is right now. It is just for us having this in a Python tracing script, for example. And in Python, we just say, okay, we attach to this net inbound message trace point with this function, which we just defined here, and say, okay, each time this function is reached, each time this trace point is reached, we execute this function in Ebpf, and then we attach to the map that we send the data into another function which we call a handle inbound here, and each time, each time something is being sent in Bitcoin Core, we call this function in Python and have even like all the data that is being sent. And that means we can get creative here. We don't have to print it here. We can have like message queues or like what I showed earlier, like terminal UIs, for example, or so, that visualize the data in some cool way. Yeah, and that's it for the presentation part. Any questions? Yes?
So how does it like hook into the binary? Is it like the trace point themselves, they actually like, how does that actually work? Is it because you've set it up, established it beforehand in Bitcoin source code?
Right, so we define, okay, we say here we want to have a trace point, and during compilation, it writes like some kind of node in the binary with a list of trace points. And then when we like want to hook into them, we say, okay, we want to find this name, this trace point with this name in this list, and it shows us, okay, here's the address in the binary. And then the kernel does magic and says, okay, each time this address is reached, we're going to stop, execute the Ebpf script, and then continue the Bitcoin Core. Okay. Yeah.
As like new features are added or new functionality, would they have to add additional trace points if they wanted to look into that?
Yeah, correct. So and we have like a bunch of trace points right now but we cover like definitely not everything there is. Okay. And there's like a lot of trace points that we could add or can add. There's still like, I don't know, like there's a list of like 20 things or so, like an issue on Bitcoin Core. where we list just trace points that we could add but haven't gotten around to. And yeah, if there's new functionality and somebody implements it and says, okay, I'm just going to implement the trace points for people to like use it in vViewer, so that makes things a lot easier for people, I think.
And does it add any sort of like overhead or latency?
That's a good question. Doing like you can compile Bitcoin Core without trace points, then there is totally no overhead.
Yeah.
And you can compile Bitcoin Core with trace points. Then there is really small overhead of like the arguments. For example, let me see. So for example, like this function is being executed. Yeah. The connection type as string is being executed. Yeah. But if you don't end up doing anything with it, then this is definitely overhead. Yeah. And if you hook into the trace point, like is compiled in and you hook into it, then you have the overhead of the switching to kernel. Yeah. And the overhead of executing the kernel program. But you often, like, if you actually do tracing, then it's fine for you to have those really small overhead. And this is a method of having like really small overhead going via the kernel and sending it out asynchronously to the tracing script, for example. Yes. Yes.
Which data types can be passed to trace points?
Oh, actually, good question. Yeah. We're a bit limited. We're like basically like all data types that are defined, for example, C strings or integers or something like that. But we can't pass, for example, objects or C++ classes to it, because on the other hand we have like a C script here or like a C program here, and we can't do anything with like C++ strings in C. That's the limitation here. So that's why we use the function C string here to pass it as C string to the C script and not as C++ string, because they're quite different. Yeah. Yes?
I guess I'm struggling a little bit to understand why you wouldn't just add this stuff to one of the existing interfaces like RPC or REST or what's the motivation in creating a new interface?
So, well, the REST interface is more, or the REST and RPC interface is more, you do a call from a client and you get data back, but you don't have like the real-time message passing. That's more something you have in the CMQ interface. But then again, CMQ is quite different from it. Well, there's definitely a point that you could have some tracing functionality over CMQ as well. Just our current implementation of DMQ doesn't really give that away, or isn't really like the best solution for that. Okay. So now the hands-on tracing part begins. I should have sent all of you that sent me a pubkey till, I don't know, this morning, a server name. And if you had to, like the notes and the task for this workshop on v23.0/Ebpf, then you're going to find like a list of server names mapped to IP addresses. So you probably should be able to log into your server, which is actually the first task here. And if there are anyone else that I think I just saw somebody sending me like a new new pubkey. I'm probably going to set up a few more people in the meantime, and then we'll be back once you did task 0. I have a few questions just for you to get familiar with the server. If you don't have access to a server and you haven't sent me a pubkey yet, either you sit with somebody who like has access to it and you work with them, or if you're interested, you can just follow along, or you, I don't know, go to some other workshop. Yeah.
The server name you gave us.
Which kernel version does the server I provided have? 5.10, yeah. Does anyone know why this is important?
Needs to support all of this that you're doing.
All right, so yeah, the tracing and like Ebpf things are like under development, and like since 4.8 or so, like the basics are in, but they still add like new features and everything. So it could be that you run like if you do this at home or something somewhere else, that you have like an old kernel version and not everything is supported, but it should be in the I don't know next year or so, once you upgrade your operating system. And yeah, how much memory does the server have? 4 gigs, yeah, correct. And were you able to switch to the root user? Okay. Does anyone know why this is important? Yeah, so the issue with the Ebpf and loading stuff in the kernel is you need special permissions. You technically you don't need to do it as root user, and you probably don't want to do it in your own machine, but it's an easy way for us. And since you all like BPSs, I'm going to destroy afterwards. It's an easy way for us to do it during this workshop. Okay. How are people on the second task or the task 1? How far are you? Okay, we're going to wait a few more minutes.